So this lecture is about inequality constraint optimization. In addition to the previous constraints that were equality constraints, now we are going to deal with inequality constraints. And that's going to affect the way that we formulate the Lagrangian and also the KKT conditions. So after this lecture, our goal is one, to be able to formulate the KKT conditions for an inequality and equality constraint optimization. We also want to understand the difference between binding and non-binding inequality constraints. All right. So first, I'm going to review the scenarios that we discussed before. First, we discussed about unconstrained optimization, which is basically minimizing a function with variables x. Then we talked about equality constraint optimization problem, which is minimizing a function like f of x subject to g of x is equal to 0. After this, in this lecture, we are going to talk about inequality constraint optimization, which is minimizing a function that's variables are x subject to a set of inequality constraints. So the first step to solve the inequality constraint optimization problem is to formulate Lagrange function. So this is Lagrange function. The way that we formulate Lagrange function is f of x plus a vector of Lagrange multipliers for inequality constraint multiplied by each constraint. If we expand this, it's going to be f of x plus mu1 h1x plus mu m hmx, where we have m inequality constraints. All right. Now we want to minimize the Lagrange function. Minimize Lagrange function. What do? We find the gradient of Lagrange function. So derivative of Lagrange function with respect to x is derivative of f of x with respect to x plus derivative of inequality constraints transpose multiplied by mu, which is equal to 0. Again, I would like to remind that mu is a vector of Lagrange multipliers. All right, and then we find the derivative of Lagrange function with respect to mu, which is h of x, and this should be less than or equal to 0. We also have an additional constraint, which is the diagonal matrix mu multiplied by derivative of Lagrange function with respect to mu should be 0. And if I want to expand this, this is nothing but mu1 multiplied by the first inequality constraint should be 0, mu2 multiplied by the second inequality constraint should be 0, and mu m multiplied by the m's inequality constraint should be 0. So these are the KKT first order or necessary conditions. So now the question is about whether our constraints are binding or they are not binding. What does that mean? Let's say we are talking about constraint h of x less than or equal to 0. So this, and the corresponding Lagrange multiplier, the corresponding Lagrange multiplier is mu. So if you look at the KKT conditions, we had mu multiplied by h of x should be 0. But something that we want to note here, either mu or h of x should be 0. They cannot be 0 at the same time. How do we do that? We define two scenarios. Binding constraint, non-binding constraint. So if we have a binding constraint, it means h of x is equal to 0 at the optimal point. Let's say I call the optimal point x star. So h of x star is 0. In this case, mu should be positive. It cannot be 0. Non-binding constraint, what does that mean? It means your constraint is strictly less than 0. So h of x is non-zero. In this case, in order to make sure that this equality holds, mu or your Lagrange multiplier for the corresponding inequality constraint should be 0. So what we can conclude, Lagrange multipliers for inequality constraint is either greater than 0 or equal to 0. If it's greater than 0, then it means our constraint is binding. If it's equal to 0, it means our constraint is non-binding. All right, now let's take a look at an example. We have minimizing x1 squared plus x2 squared subject to x1 plus x2 is equal to 1 and x1 is less than or equal to 2. All right, so in this case, we have both equality and inequality constraints. Let me define one more inequality constraint, x1 plus x2 less than or equal to 7. All right, so now what we have to do first, we have to assign some Lagrange multiplier to each constraint. So for this one, I call it lambda. For this one, I call it mu1. For this one, I call it mu sub 2. So what's going to be our Lagrange function? F of x plus lambda transpose h of x plus mu transpose g of x. We can call, let's do this for the sake of notation. Let's use g of x for equality, h of x for inequality. So given this, our Lagrange function is going to be x1 squared plus x2 squared plus lambda multiplied by x1 plus x2 minus 1. So this one leads to x1 plus x2 minus 1 is equal to 0. We call this g of x. This one leads to x1 minus 2 less than or equal to 0. This one is h1x. This one is x1 plus x2 minus 7 is less than or equal to 0. So we call this h sub 2 of x. All right, plus mu1 multiplied by h1, which is x1 minus 2, plus mu2 multiplied by h2, which is x1 plus x sub 2 minus 7. So now that we have Lagrange function, we can write the KKT conditions. First KKT condition is derivative of L with respect to x1, which is going to be 2x1 plus lambda plus mu1 plus mu2. Then we find derivative of Lagrange function with respect to x2, which is going to be 2x2 plus lambda plus mu2. Then we find derivative of Lagrange function Lagrange function with respect to lambda. This one should be 0, this one should be 0. So when we find it with respect to lambda, it's basically our equality constraint, 0. There are two more cases. One, derivative of Lagrange function with respect to mu1, which is x1 minus 2, should be less than or equal to 0. This is one of our inequality constraints. And the other one is derivative of Lagrange function with respect to mu sub 2, which is our second inequality constraint. There is one more condition, which is actually two conditions. So one is mu1 multiplied by x1 minus 2 should be 0. Second is mu2 multiplied by x1 plus x2 minus 7 should be equal to 0. We also know that our mu's are greater than or equal to 0. So mu's, mu1 and mu2 are greater than or equal to 0. So let me go over it one more time. We have this optimization problem. This is your objective function, or f of x, which is in this scenario f of x1 and x2. We have our equality constraint, or g of x. We have two inequality constraints. In this case, we call them h sub 1 of x and h sub 2 of x. Then we define Lagrange multipliers that correspond to each of these constraints. For example, lambda corresponds to the equality constraint, mu sub 1 corresponds to the first inequality constraint, and mu sub 2 corresponds to the second inequality constraint. Then we define the Lagrange function. This is nothing but your objective function plus equality constraint Lagrange multipliers multiplied by the equality constraint plus inequality constraint Lagrange multipliers multiplied by the inequality constraints. After we formulated the Lagrange function, we want to write KKT first order or necessary conditions. In order to do that, first we find the partial derivative of L with respect to our variables. So partial derivative of Lagrange function with respect to x1, with respect to x2. Then we find the partial derivative of our Lagrange function with respect to the Lagrange multiplier of equality constraint. We put all these three, all of this to equal to 0. Now we have to find the partial derivative with respect to mu sub 1 and mu sub 2, which are inequality constraint Lagrange multipliers. and they should be less than or equal to 0, which is the same as our inequality constraints. Here is this set of constraints. Also, this is for determining whether the constraints are binding or non-binding, right? So we have mu sub 1 multiplied by the first inequality constraint should be 0. Mu sub 2 multiplied by the second inequality constraint should be 0. We also have an additional constraint which tells us mu sub 1 and mu sub 2 both should be greater than or equal to 0. Now going back to our definition of binding and non-binding, if mu1 is 0, then h sub 1 cannot be 0. It should be less than 0. If mu1 is non-zero, then x1 minus 2 should be equal to 0. We are going to talk about this in future lecture when we solve some examples, but this is the way that we can formulate the KKT conditions. So now that we became familiar with inequality constraint, I'm going to write a general problem. So in this lecture, we talked about inequality constraint, but I'm going to talk to formulate a general inequality and equality constraint optimization problem. So we have minimizing f of x subject to g of x is equal to 0 and h of x less than or equal to 0. So we correspond Lagrange multipliers corresponding to the equality constraint. We call them lambda. We define Lagrange multipliers for the equality constraint equal to 0. So first, we determine our Lagrange function, which is f of x plus lambda transpose. Actually, yeah, lambda is a vector of Lagrange multipliers, and mu is also a vector of Lagrange multipliers, multiplied by g of x plus mu transpose multiplied by h of x. In the next step, we determine the KKT conditions. First, we have to find gradient of Lagrange function with respect to x. So if we have multiple x, it's going to be with respect to x1, x2, and so on. So this is going to be gradient of f of x with respect to x plus gradient of h of x with respect to x transpose multiplied by mu plus gradient of g of x with respect to x transpose multiplied by lambda. This is the generic form. And then we have gradient of L with respect to vector mu, which gives us a set of inequality constraints. We have gradient of L with respect to lambda, which gives us our equality constraints. And also we have the diagonal matrix with mu on the diagonal elements multiplied by gradient of L with respect to mu, which is nothing but diagonal of mu multiplied by h of x is equal to 0. We also have another constraint about mu's. Mu's should be greater than or equal to 0. So this constraint here, this one, we check the combinations of binding and non-binding scenarios. to determine what's the optimal solution. So this is the way that we can find the KKT necessary or first order conditions for equality and inequality constraint optimization.